So friends, welcome to my another session. This is on chromophores and auxochromes. And also another topic what we are going to discuss about here is the effect of conjugation. Kindly make sure that you see my previous videos on this electronic spectroscopy or UV visible spectroscopy. Then later you come to this one. And also I want to inform you that this video is particularly useful for the degree students of chemistry for spectroscopy chapter. And this is the final video as part of UV visible spectroscopy. Now we will discuss what are the chromophores and what are the auxochromes and how the conjugation will affect the absorption of UV visible light. Now we will move on to the chromophores definition. This chromophore is if you say simply, it may be an atom or group of atoms. We can say like this, it's a functional group. The functional group of the molecule which is responsible for absorption of UV visible light is called as chromophore. So this is the functional group, or it may be a part or region of a molecule which is because of which the molecule absorbs the UV visible light. That portion of the molecule is called as chromophore. Because of this chromophore, the molecule absorbs the light, UV visible light, and as all we know, this UV visible light is responsible for the color of the substance. So color is because of the chromophore. For example, if you see the examples here, the ethylene, CH double bond CH, that means double bond, carbon-carbon double bond, and acetylenic means carbon-carbon triple bond, and carbonyl function, that is C double bond O, and acid, C double bond OH, ester, C double bond OR, and nitrile or cyano, that is C triple bond N. All these compounds, if we observe, all these groups containing either pi electrons or pi and non-bonding electrons. If you see the alkene, that is CH double bond CH, it is having pi bond. Acetylene is also having 2 pi bonds. Carbonyl function is having pi bond between carbon and oxygen, and also oxygen is having lone pair of electrons. Like that, similarly, acid, ester also contains carbon oxygen double bond, and also oxygen having pair of electrons, 2 pairs of electrons. So nitrile group is C triple bond N. Here the carbon and nitrogen are having 2 double bonds between them, total 3 bonds, and the nitrogen is having a pair of electron on it. So therefore, because of pi electrons means pi bonds, and because of n electrons, that means non-bonding electrons, the transitions will take place. So these chromophores accordingly can be classified into 2 types. One type, they are having only pi electrons, and if the molecule or if that particular functional group is having only pi electrons, then pi to pi star transitions will occur. If both non-bonding electrons and pi electrons are present, then there is a possibility for 2 types of transitions, that is n to pi star and pi to pi star. So in our last video also we have seen what are the different types of electronic transitions and how they will arise. All these things we have discussed. So if you have any doubt, kindly refer to my previous video. So here in this slide we can see the different examples, simple examples of chromophores, different chromophores. First example is benzene. Benzene is having 3 alternate double bonds, so therefore pi to pi star transitions are possible, and its absorption energy is at 210 nanometers. Similarly, in the next example, what we wrote as styrene. So there is extended conjugation. Extended conjugation means 3 double bonds are there, and there is another pi bond. The another pi bond is this one. This is the another pi bond. So this is an extra pi bond. because of which the energy absorption is going to 250 nanometers. And also there is benzoate ion, some ester. Here also benzene ring is having 3 double bonds, and there is a 3 double bonds, and there is a carbon oxygen double bond is there. So therefore, and it is having 230 nanometers of energy. And in next example, naphthalene, so we are having 220 nanometers of energy absorption, and anthracene 250 nanometers of energy absorption, and alkenes some 190 nanometers of absorption. And there are dienes. Diene means 2 double bonds. 2 double bonds are present in the molecule, therefore it is diene. One is absorbing at 220, another is 240, and there is a molecule having carbonyl functional group C double bond O, and the C double bond O functional group is absorbing the light energy at 280 nanometers. And here this is a enone. Enone means there is a double bond, and there is a one means ketone. C double bond O group is there. So therefore 250 nanometers is of double bond, and 310 nanometers is of because of N2 pi star transition. So like this, different molecules having pi electrons and N electrons are acting as chromophores because they are absorbing the UV visible radiation. So in this way, the chromophores absorbs the energy. Now we will go to the concept called auxochromes, and this auxochrome is, it's a sometimes it may be an atom, or sometimes it may be a group of atoms. On its own, it cannot absorb the UV visible light, but whenever the auxochrome is attached with other chromophore, then what it will do, it will it will alter, or it will change the absorption energy of the chromophore. That means when it is attached with a chromophore, it modifies the absorption wavelength of the chromophore. On its own, it cannot absorb the UV visible light, but whenever it is attached to a chromophore, it modifies the absorption wavelength of the chromophore. The examples include hydroxy, OH group, amino, NH2 group, and ether group, OR group. So these groups are generally they act as auxochromes, and whenever they are attached with a chromophore, then they will alter the absorption wavelength of the chromophore. And one more fact is that the auxochrome generally contains, oxygen, nitrogen, halogen, or sulfur. So these heteroatoms, that means extra atoms other than carbon and hydrogen, that is oxygen, nitrogen, halogen, these are responsible for altering the energy of absorption of chromophore. And these oxygen, nitrogen, halogens, whenever they are present, generally they are acts as auxochromes. So as you know, as they are altering, because of this alteration, because of this change of the wavelength of absorption of the chromophore, the color of the compound intensifies. Intensifies means the color becomes more brighter, or you can say the color becomes more intense. So in that way, these auxochromes help the chromophores to make the molecule, or to make the substance more colored substance. And as one more point here is, this one we will discuss in the effect of conjugation also, the last point. These auxochromes lowers the wavelength of absorption value. That means, as if, let us say for example, a chromophore is absorbing the light at 250 nanometers. Then whenever auxochrome is attached with it, that means whenever the auxochrome combines with a chromophore, the energy absorption value increases, the energy value will be decreased and wavelength will be increased. That means wavelength may be greater than 250. That means without a chromophore, without an auxochrome, if the chromophore is absorbing the wavelength at 250 nanometers, then because of the auxochrome, whenever we add auxochrome to it, it may absorb the light energy at 260 nanometers, 270 nanometers, 280 nanometers. That means more than 250. So it lowers the energy, therefore it increases the wavelength of absorption. And this lowering of energy or making the chromophore to absorb more wavelength radiation is called as bathochromic shift. Bathochromic shift or red shift. And it increases the lambda maximum of the chromophores, as we have seen. So there are a set of rules called Woodward-Fisher rules. Woodward-Fisher rules. And these Woodward-Fisher rules are useful to predict what might be the new wavelength of absorption. That means if you add some auxochrome to a chromophore, then how this auxochrome will alter, how much it increases the wavelength of absorption, that can be known by these Woodward-Fisher rules. And we can see the two types of auxochromes here: acidic auxochromes, OH, COOH, SO3H, and basic auxochromes, which are having basic nature: NH2, NHR, NR2. As we know, OH, COOH, SO3H, these are acids, and NH2, NHR, NR2, these are the amines, primary, secondary, tertiary amines. These are the amines are the basic compounds. So simply we can, like that, we can classify them as acidic and basic. So as we have already discussed, auxochromes intensifies the colors of the substances. And here see the example, the benzene lambda maximum is 255 nanometers. Whenever we are adding OH group to benzene, that means whenever we are adding an auxochrome OH, then the lambda maximum is increasing from 255 to 270. So this is 255. This is only benzene. That means only chromophore. Whenever you add a OH group, then the lambda maximum is increasing from 255 to 270 nanometers. In a similar way, if you add an NH2 group, then the lambda maximum is increasing from 255 to 280 nanometers. So in this way, we can see the effect of auxochrome on lambda maximum value. So whenever you attach an auxochrome, then lambda maximum value will increase. Similarly, in the second example also, so this is a simple pi system which is having 190 nanometers of absorption. Whenever you add some NH2 group, an auxochrome, then the lambda maximum is increasing to 230 nanometers. So in this way, the effect of auxochrome will be there. Next one, So next one, we will go to the effect of conjugation. Conjugated system is the one in which electrons in pi orbitals are in delocalization. Conjugated system means, so in that system every carbon will have a p orbital, and the electrons will move around these p orbitals of all the carbons. So that is the conjugated system. We will see the next picture what it is. Here we can see the p orbitals all are having, each and every carbon is having a p orbital. This is 1,3-butadiene example. Here C1, C2, C3, C4, each and every carbon is having a p orbital with one electron, and these electrons will delocalize. Delocalize means they move from one carbon to the other continuously, and this is called as delocalization. And whenever you find a delocalized system, that is known as a conjugated system. So system having alternate single and double bonds also can be called as conjugated system. So carbons having alternate single and double bonds, or single and triple bonds, single bond, double bond, single bond, double bond, single bond, double bond. So these type of systems also can be called as conjugated systems. Sometimes carbocations means carbon having positive charge, carbon radical means carbon having a single electron, and lone pair of electrons present. All these electrons also may be involved in the conjugation to make it a conjugated system. The important point what we have to remember here for this conjugated system is, because of conjugation, energy of the system decreases and stability of the system increases. This is the very important point what we have to note down. So because of the conjugation, that means because of this delocalization of electrons present in p orbitals, the energy of the system decreases and stability increases. As we know, in resonance theory also we will check this point, that because of resonance the stability of the system increases. Resonance is also nothing but movement of electrons from one place to the other place. Similarly, because of this conjugation, the energy of the system decreases and its stability increases. You have to remember this point. See, then this is the 1,3-butadiene example. Here 4 carbons are there, C1, C2, C3, C4, and each carbon is attached to a double bond, and every 2 double bonds are separated by a single bond. C1, C2 are having double bond, C2, C3 is having single bond, then C3, C4 is having double bond. Therefore, we can give an example as a example for this conjugated system. See, another point we discussed, carbocation, carbon having positive charge, carbanion, carbon having negative charge, atom with a lone pair, here in oxygen having 2 lone pair of electrons, radicals means carbon having a single electron. They also sometimes involve in delocalization, that means movement. So see, here in carbocation, this pi bond is moving between the carbon having positive charge and other carbon, and this positive charge is moving, and because of this movement we can say that it is a conjugated system. Here the carbanion having negative charge, it is also involving in resonance or delocalization to give conjugated system, and here the electrons present on oxygen are involving in a conjugation, and here the radical single electron which is present on carbon is involving in this conjugation. So therefore conjugation may be present sometimes in carbocations, carbanions, atoms with lone pairs, radicals. So these are systems also can be called as conjugated systems. Then the important point here is, as the number of conjugated pi bonds increases, the energy difference between the ground and excited state decreases, and because of that the absorption wavelength increases. Longer wavelength means higher wavelength. So as the conjugation increases, the lambda maximum value increases. We can see this point, or we can observe this point in this example. Here 2 double bonds are in conjugation, 217 is the lambda maximum. Here 3 double bonds are in conjugation, so the lambda maximum is increasing to 268. Here more number of double bonds are in conjugation, and therefore the lambda maximum is increasing to 364 nanometers from 217 nanometers. So that means as the conjugation increases, as the conjugated double bonds increases, the lambda maximum value increases, because the systems becomes more stable, less energetic. Less energetic means more wavelength. So therefore as we know, energy and wavelength are inversely related to each other. So in this way the wavelength and energy are inversely related to each other, and as the double bonds increases, alternate double bonds or conjugated double bonds increases, the lambda maximum value increases. Here also we can see the phenolphthalein example, generally where we what we will use in our laboratories. Phenolphthalein will have a pink color in basic medium and colorless in acidic medium. That means pH around 0 to 7, pH colorless. Whenever the pH increases more than 8, that means whenever the solution becomes basic nature, then phenolphthalein will get pink color. This pink color means it is absorbing the UV visible light. That means its lambda maximum is increasing than in colorless form. This increase in this pink color is because of the extended conjugation. See, double bond, double bond, double bond, double bond, double bond, double bond, double bond. All these bonds are in conjugation. Every 2 double bonds are separated by a single bond. So therefore there is an extended conjugation here. Because of this extended conjugation, it is able to absorb the UV visible light, and it is appearing in pink color. Whereas in colorless form, there is no conjugation. That means each and every individual benzene rings are having conjugation, but in between them there is no conjugation. But whereas in this form, that means basic medium form, it is having conjugated because double bond, single bond, 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 double bond. So extended conjugation is there. Because of this extended conjugation, this phenolphthalein is getting pink color in basic medium. So that is one point. The ring is getting open, that lactone ring, in colorless form, and because of this ring opening, it is becoming more conjugated or extensively conjugated, and it is becoming pink colored substance, phenolphthalein. And this is beta carotene, which is responsible for the this red color or orange color of carrots. And beta carotene, this is also having extensive conjugation. We can see the extensive conjugation here, double bond, double bond, double bond, and each and every double bond are separated by single bonds. So therefore beta carotene is the responsible for color of carrots, and because of this extended conjugation, it is able to absorb the visible light. So in this way we can discuss how the conjugation will affect the absorption wavelength. As the conjugation increases, absorption wavelength increases, the system becomes more stable, the system becomes more colored because of this absorption. Because as the conjugation increases, the energy or the stability of the system increases or energy decreases, and it absorbs less energy also. So less energy means more colored according to this UV visible concept. So in this way we can once again summarize our points here. What are chromophores, examples, what are auxochromes, examples, and how the auxochromes will affect the lambda maximum of the chromophores, and what is conjugation, how this conjugation affects the absorption value, and how it gives the colors, and all these things. So thank you for watching, and kindly subscribe to my YouTube channel, where you will find the other videos of this one, and we will try to make the other videos also which will be useful to the student community. Thank you very much.